We'll make Gaelle pay. Oh my goodness. Germans, they break French breaking.
Attends.
It's like Napoleon.
Attends, attends. Voilà. C'est bon? Ouais, ouais, vas-y, vas-y.
Okay, so hi everyone, and welcome to the sixth talk of this lecture series, these seminars in medical informatics. We've had a variety of topics and a variety of different backgrounds of speakers, and today is no exception. And we have the honor of having with us Professor Gaelle Calvary, professor in computer science in Grenoble and in the Grenoble Institute of Technology. Professor Calvary has been working on a topic that I think can be very, very relevant for medicine in the future and all these big data that we so often talk about regarding health and medicine and healthcare. We have too much information. What can we do about it? We had talks on different ways to address this problem. This is a very interesting way, and it's very closely related to our human-computer interaction class. I think this is a very interesting talk. Thank you so much, Gaelle, for coming here. And so I asked Professor Gaelle Calvary if this should be more interactive, if you can ask questions in the middle, or we leave all the question and answers to the end. And Professor Calvary prefers that this is more informal. You know, if you want to make a comment, and don't leave everything to the end. So if you feel like making a comment, you know, we can interact in the beginning. Then if it becomes too late, then I'll ask to stop. But you know, this is much more interesting if there's a dialogue. So again, Gaelle, thank you so much. The floor is yours.
Okay, thanks a lot. Thank you very much, Miguel, for this invitation. Thank you very much to everybody for being here. So my background is computer science, and my research area is about human-computer interactions. That's why I prefer interactive talks. Of course, they must be consistent. Huh? So do not hesitate to interrupt me if it's not unclear. If my accent is too French, no problem. I try to adapt myself. So instead of presenting you plastic medical user interfaces, I've decided to convince you that it's highly important to have transdisciplinary research, cross-domain research, so that to learn from other disciplines. And so the decision I took is to show you what plasticity in medicine means and how we import this concept into computer science so that to invent a new generation of user interfaces. And we can do exactly the same with plasticity of materials, for example. And really, my way of working is to be always open-minded as much as possible, of course, and to try to learn from others and all together to make things we can't do alone. That's really the way I appreciate to work with my students and colleagues. Of course, what I present here is not my own work. It's a collaborative work with so many students. And in particular, one student who was at the end engineer in computer science, software engineering, and who decided to continue so that to become doctor in medicine. And so in France, it's possible to move from one discipline to another one, and more people are encouraged to have such courses. So I incorporate that in my slides so that to show you how it's possible to work with this open mind vision. So first of all, thanks to Miguel and Daniel for this very kind invitation. So I come from Grenoble, Grenoble in English, but Grenoble en français. So Grenoble is here. So you see it in the Alps. So we have snow right now. It's a beautiful place. I'd be happy to invite you in Grenoble, and I'll take care of you as much as you did here. And it was really a pleasure. And this summer, we will have a new building for research in informatics, for our lab, and just to give you some figures, we are a huge French lab in informatics in Grenoble. We are nearly 500 persons, so you see it's a huge lab. I am deputy director of the lab. This lab is made of 500 people, so of course it's not possible to present all the topics that are considered in the lab. But to make it quick, I can say you that people are organized into 20 research groups, and so that to cover 5 main research axes. So for example, formal methods, models, and languages. So computer science, distributed systems, parallel computing and networks, data and knowledge processing at large scale, software and information system engineering, and this axis, which is about interactive and cognitive systems. I do my research in this area. And all these 5 axes together work together really, so that to make progress in one single scientific project, which is about the ecosystems, heterogeneous and dynamic ecosystems made of humans, physical systems, and of course also software applications. So human digital ecosystems are is the title of our scientific project. We all together, so 500 people address. Yes, we are all in Grenoble, and we will be in this new building in the summer. Up to now, we are splitted in 9 buildings, and so it's not so easy to collaborate all together. And so in the summer, we will have a new building for everybody, plus other labs. One lab about mathematics, and another one specialized in embedded systems. And altogether, we will be around 1,000 persons in one lab, so that to do things we can't do alone. Yeah, so please visit us. It will be a pleasure to have you in Grenoble for sure. Okay, so you see we have 20 research groups. One of these groups is called Engineering Human-Computer Interaction, and it is in these groups that I do my research. We are nearly 10 permanent members. So Yann Miguel is this person, Yann Loriot, you know, okay? So one of these persons I collaborate with. And altogether, what is of interest for us is the phenomenon of interaction between users and systems made of physical hardware and also software pieces. And of course, it's not possible to study interaction without putting together, or of course, computer science, because in our lab we are all computer scientists, but also people from cognitive science, psychology, sociology, and also medicine and such experts, depending on the applications we target. And so in our lab, we are computer scientists, but we collaborate with all our other labs in Grenoble, in France, and in Europe have in our lab. And so the point is to accelerate the interaction so that to make it possible for the user to quickly get the right contact at the right time and so on. So for example, this is a research that was done in our team. About the user interface, we have one expert in interactive visualization. So the point, big data, we have so many data. So how to make it possible for someone to learn from data, that means to discover things that are not easily discoverable when looking at all these data. And so he invents new interactive visualization so that to data, for example, the tree maps he proposed, so it's Renault Blanc, and so you interact with data, so it looks like semantic zoom, and so really the point is to make it possible to navigate among this large set of data and to learn from these data sets. And we also have people that address the system as a whole, and that, for example, covers this area of end-user programming. So, for example, at home, you have old persons who want to program their quality of life. For example, I want to get a coffee at 7 o'clock when waking up. And so how to make it possible for someone who is not computer scientist to program rules for living in a house. So that's the research area, which name is end-user programming, so by non-experts. And in addition to types, different focus of research, people who are specialized, for example, in graphical user. My research area is about plasticity. Is granularity ranging from the interaction device to the system as a whole. And so plasticity is defined in other areas, for example, in the materials area, and you probably know this picture from Salvador Dali. You have the clock that adapts to the situation. And what is interesting is that it's still possible to know what time is it. So this clock is still usable despite the deformation. That's a kind of plasticity. And so I investigate that, not in the domain of the materials, but I import this concept into computer science. And my question is, what could be a user interface that is plastic, that means that adapts to its situation, the situation being the end user's skills, for example, the language, the level of expertise, but also the environment. It is noisy. There is this level of light, for example. And also the platform. You know that the user interface can't be the same on a large surface versus on a small
task. The excitability of neurons distant to these regions heightens. And after weeks of practice, certain cortical maps representing the body parts being used enlarge to include adjacent, previously uninvolved areas. These findings suggest a process we call plasticity, the brain's ability to change in response to our experiences, its ability to learn. The supplementary motor area, also known as SMA, and the primary motor cortex, also known as M1, are the main areas involved in task learning. A highway of neural connections carries information from SMA to M1. However, many of these pathways are inhibited by signals from local GABAergic neurons that synapse densely around pyramidal cell bodies in M1. But disinhibition can occur. With focused repetition of a motor task, high-frequency activity is induced in thalamic projections to M1. And if input from SMA arrives at the same time, these inhibitory signals to the excitatory pyramidal cells of M1 diminish. Pathways once latent now activate the caudal part of SMA. And as practice of the task continues, activation spreads to the rostral area. Meanwhile, changes are also taking place in M1. Within M1, sprouting at axons and dendrites creates new synapses or strengthens existing neuronal connections, resulting in greater complexity of the effective neuronal network. Those pathways less used may be weakened through long-term depression, while those used most frequently may be strengthened through long-term potentiation. Several weeks of practice revealed growing representations of the body parts being used. Their boundaries, once considered static, begin to show overlap. As proficiency at the task increases, unnecessary neurons become inhibited. Cortical areas in M1, once enlarged, shrink to optimal sizes, and activation in SMA decreases. The brain is finding the most efficient use of space and neurons, and the student is learning to master the skill. In the young pianist learning a piece, as in the recovering amputee reacquiring an old skill, research is uncovering similar plastic mechanisms at play, knowledge of which we may one day use to speed recovery from injury and disease, and with some persistence, even surmount disorders of memory and learning.
And so we read a lot of publications, and then we decided to create a word cloud so that to see the key words in the domain. And it's funny because we have exactly the same in computer science in the domain of plastic user interfaces. So we see that there are two key dimensions, space and time. And about space, we have precisions, brain, and so on. We see that the notion of task is key, and it was also mentioned in the video. The notion of area also. And then look at that. All the modalities that are mentioned, there is a lot of publications about the modalities that are involved in the plasticity process. And the ultimate goal can be to improve performance of the user when performing the task, or to improve user experience. And these words, we have them also in human-computer interaction. And more precisely, beyond this word cloud, we selected this definition of brain plasticity. So it is a process, a continuous process, allowing short-term, middle-term, and long-term remodeling things from medicine, okay, so that to optimize something. And we have exactly the same concepts in human-computer interaction with three added value, three goals, which can be to follow the natural evolution of the person, but also to support experience and learning, or also for rehabilitation. And what is changed in the plasticity process can be the structure of the network or the functions it supports. There are different types of plasticity, three types: sensory motor, cognitive, emotional. Most publications we read were about sensory motor plasticity, with distinction between intramodal, multimodal, intermodal, and metamodal. And these terms, we have them also in human-computer interaction. And we also get this information that doctors identify different levels of integration of the plasticity process, time being always key. And the different levels of integration we saw in publications range from the molecules, so very fine level of integration, synapse, cellular body, axon and dendrite, neural network, brain, to the body as a whole. And so then we try to structure the concepts we read in the paper into the two dimensions, which are the space integration level and time. So we got this classification of the concepts from medicine, and then we looked at the research done in computer science about plasticity, so that to see the holes, that means the research we should now do so that to take benefit from cross-domain research. And so in human-computer interactions, the approach we had is really centered on the interaction between two entities. We have the user who is plastic, okay? So we have a plastic user. The user is plastic by definition. And our challenge in human-computer interaction is to create systems that are plastic in the sense that they will adapt to the user while interacting with this system. And really the point is to either increase user experience or increase performance, but really to make the user change depending on the context of use. And so more precisely, you have a user who interacts with the system. So the user is in blue and the system is in green. Whatever the entity is, we have this basic process of perception, decision, action. So the user perceives his context given the task he has to do. And when I say he perceives his context, that means also that he perceives the system he is in front of. And so he has this process of perception, decision, action, and probably an action on the system he interacts with. And in turn, the system perceives the action performed by the user, decides a reaction to trigger, and applies this reaction he decided to for example, to give as a feedback to the user. And again, we have this loop of interaction between the user and the system. And what is of interest for me is to add the adaptation dimension. So it's not only to interact with the system, but also to adapt, including all the things that happen when interacting with the system. And so the point is to predict from experience. That's really the plasticity dimension that I am interested in. So people in medicine investigate this dimension. The dimension I am interested in is a similar dimension, but from the system point of view. And my challenge is to develop algorithms that make it possible for the system to predict what the user wants to do and to learn from user action so that to adapt, to anticipate user action and to adapt the system accordingly so that to increase user experience. And so really this red box, this red loop is the loop of interest. And what is difficult is, of course, that we have this co-adaptation, global co-adaptation with this dimension of interaction plus adaptation that are difficult to separate. And so that's the theoretical framework I work about, and I try to identify the properties we must satisfy so that to ensure the quality in use that is expected by the end user. So it can be supporting natural evolution of the end user. It can be support his experience and learning. It can be improve his rehabilitation, if I go back to all the terms that you have in medicine. And so, for example, if I assume that the challenge of plasticity is to increase user performance, we know we have this basic curve in human-computer interaction. We know that it is easy to deliver a simple interaction for a limited number of functions. If your system is limited to a compute, 2 plus 3, the function is limited, and of course, the user interface can be simple. Okay? The complexity comes from the number of functions you want to support. If you want to support a large set of functions on your so small device, the risk is, as a result, to get a complicated user interface because the challenge is difficult. You want to support a large set of functions, and it is difficult to provide a simple interaction because it's difficult to do simple. Okay, this is the curve we have in human-computer interaction. The challenge in human-computer interaction is to move. We can't change this curve. That's logical evolution. So the challenge we have in human-computer interaction is to move the curve in this way so that for a given number of functions you want to support, because these functions are relevant to the end user given the task he has to accomplish, the point is to move the curve in this way so that for this number of functions you want to support, instead of delivering this complexity of user interfaces, you can make it simple. That's the challenge we have. That's a challenge we have when doing research in human-computer interaction. Thanks to plasticity, my challenge is to limit the number of functions as much as possible so that to just deliver the functions that are relevant at a given time to the end user. And by doing so, it's possible for me, as I limit the number of functions by just pushing the right functions at the right time, at the right place, instead of getting, you see, this level of simplicity. Without plasticity, I have that, and with plasticity, I have that. That's the challenge I have if I focus on performance. Okay, I can focus on rehabilitation, so it's another challenge. But if I reason on performance, that's exactly the theoretical framework, and so the challenge we have to when doing research. And what is interesting in plasticity is that as you deliver systems that are capable of self-adaptation, it's easier for the designer, as now the system is in charge of redesigning itself at runtime. Until now, the strong hypothesis, when you use all your mobile phones here, the strong hypothesis is that at design time, you have complete and correct specifications of the system. And so you have someone in charge of doing an analysis, writing specifications, coding the system, evaluating the system, integrating the system, deploying the systems, finished, and you cross the fingers so that the guy is happy with the system. No adaptation, the system is rigid. Now that we have this diversity of systems, this has a cost because you must design a system for a small screen, larger screen, and there are other modalities than visual and so graphical user interfaces. You have also vocal user interfaces, brain-computer interaction, and so we have a problem of scalability. We have a cost for developing, maintaining user interfaces for all these settings. And so without plasticity, we have to deliver one system per context of use. Thanks to plasticity, we deliver one system that then adapts itself to the situation. And that's one positive side effect, which is about cost, development and maintenance cost. And so, for example, when you, in the domain of rehabilitation, the therapists, they train, they have one specific training for everybody. Thanks to plasticity, the training would be capable of adaptation to the level, to the progress the guy has when doing exercises. And so this is really the matter of plasticity. The system adapts to the evolution of the end user. And so the system has to anticipate, has to predict, and then to adapt so that to perhaps have more challenging objectives for the end user because the progress is good, or less ambitious objectives because otherwise the guy would be depressed and stop to do training. And so that's really the challenge of plasticity, this notion of self-adaptation. And so one system for everybody, one single system for everybody, but this system is capable of adapting to the person in situation. And so here, for example, you have examples of user interfaces capable of adaptation to the platform, not to the user, but to the platform. Here you have a plastic PowerPoint with a remote controller and the slides above. And so when the teacher approaches his mobile phone, then the remote controller automatically migrates to the mobile phone so that to make it possible for the teacher to be mobile. And so you see that the user interface on the PC is not the same than on a PDA, of course. And in the same way, we have this website, for example, it's possible to connect to this website for booking an hotel. And when you connect your mobile phone, the navigation, so this bar, this navigation bar, can automatically migrate to the mobile phone so that to put all the input on the mobile phone and all the output, so the list of hotels and precision about the hotels on the PC so that to be projected on the wall and make it possible for a family to select the right hotel. And only one is clicking on the navigation bar on the PDA. So it's a kind of plasticity because the user interface is capable of adaptation to the platform the end user has, either a PC or a PC plus a mobile phone. And it's possible to couple all the capable of self-adaptation. The process can be automatic, but it can also place under the control of the end user. And for example, here you have a meta user interface, that means an additional user interface that makes it possible to the end user to say, okay, my user interface is made of a title, a content, and a navigation. And using check buttons, it's possible for him to select the devices where he wants to get these parts of the user interface. And this is completely automatic. That's why you see this user interface is not so nice because it is automatically generated. You see, it's a self-adaptation. Everything is automatically generated based on the prediction algorithm about the tasks the end user wants to do, about the perception of the interaction devices and the settings of the family. And the user interfaces are automatically generated. That's why, of course, they are not so nice than user interfaces handcrafted using 6 months, for example, by experts. And so, of course, when we speak about plasticity, we have this process of prediction, decision, and learning process that is performed by the system. And of course, the challenge is about the properties this process must satisfy, because in front of the system we have a user. The user wants to understand what happens, and so we have two meta properties in human computer interaction, which are intelligibility and controllability. Intelligibility means that the end user wants to understand what happens. That's why we have self-explanatory user interfaces that are capable of explaining themselves to the end user and justifying the adaptation decisions. And controllability, which means that the end user must be capable of stopping the adaptation process if it doesn't appreciate the adaptation that is performed. And by doing that, the system can learn from experience, because if the person rejects one adaptation, that means that the rule that was applied was not appropriate in these settings. And at a lower level, we have additional properties that are, of course, necessary so that to fully support intelligibility and controllability, which are the accuracy of the system, so that what is proposed makes sense for the end user, the previsibility for the end user, there is no surprising adaptation, stability, next time the end user will be in the same context of use, he expects the same adaptation, and transparency in the sense that he must understand what happens inside the system. And so there are several adaptations, several properties. These ones are related to adaptation, are highly difficult to support. And so if I go back to these notions from medicine, in human-computer interaction, plasticity means the capacity of user interfaces to withstand variations of the context of use being the user, the platform, and the environment, while preserving user-centered properties. So, for example, performance, or rehabilitation, or learning. It depends on the end user and the process as itself to learn the properties that are key for the end user in situation. And so up to now, what we know is that adaptation can be performed at different levels of integration, exactly like you have in medicine. And really the point is to state the problem, to understand the constraints on the solution so that the system is capable of generating a solution that means a user interface that makes sense for the end user in situation. And what we know is that the problem is defined by a task, and that was one of the words that was pronounced during the video in medicine. The task the end user wants to do, the information he needs for achieving his task. The constraints are related to the user. So, for example, his language, level of expertise, disease, and so on. The platform, do I have a PC, a mobile phone, and so on. The noise, for example, and the quality news he expects, for example, performance in general. That's what we want. And for doing that, for providing the right solution, we have to define the structure of the user interface and then to select the modalities. And if we take, for example, this very simple user interface, perhaps I go too quickly. No, it's okay. So if I use, you are familiar with this website, huh? YouTube. So it is. So this website, is it plastic? Is it plastic?
Yeah.
Why?
We can collect data from the user, and it's going to add favorite videos, let's say, in front.
Exactly.
We can choose the groups of videos, our favorites. We'll display them online.
And do you appreciate it? Is it a good system? What about intelligibility, transparency, controllability, the properties I mentioned. What do you think about that when considering this system?
I don't think so. You cannot change the layout.
Intelligibility means that you understand, for example, why the system pushes this and this video. You understand that? Are you sure about that?
This is dead or not Spotify. Putting this song because it is dead, right? I think you took
So.
Spotify does.
You can display on what you see. Yes,
What does it say? It says, I'm showing you this video because it's related to what
related
Mm.
with the type of video. If you can consider
No, but you're saying that the choice that is on the story, but that specific choice is not the only thing that we trust that somehow.
Yeah, you trust.
Tries to explain to me more like black box more like
And so a full plastic interactive system could be, should be adaptable at any levels of integration. The task could change. For example, you arrive, I don't know, I arrive in Porto, and based on my profile, services are automatically pushed because the system believes they are relevant for me given my situation. Okay, that would be a plastic interactive system at the higher level of abstraction, which is a task. And so research about services composition and so on, they are relevant for us in human-computer interaction plasticity. The task changes depending on the context of use. In terms of information, information is pushed depending on my situation. This level of abstraction means that the structure of the user interface changes depending on my situation. Typically, you see here, I have a user interface. How many parts do you believe this user interface is made of? Look at this user interface. What is the structure of the user interface? It is composed of how many parts? Who says 3? When? Where do you see the 3 parts?
search results and the action with April tendencies.
Exactly. So we have the upper part for the search, and then we have these 3 things. Okay, and this mosaic is a subpart of homepage. Okay, and so a plastic user interface capable of restructuring itself would change this organization depending on the context of use. And for example, if you do not have sufficient space on your mobile, for example, tendencies would be removed or would be accessible once you have done something. But you see the structure of the user interface changes because the context of use is no more the same. At this level of abstraction, it's not the structure of the user interface that changes, but the modalities you use. And if you decide to move from graphical user interface to vocal user interface, it is a modification at a concrete user interface level. And in general, you see the word cloud in medicine. You have many words about modalities. But in human-computer interaction, that's not the most difficult thing to do. It is at a lower level of abstraction. What is really difficult is to change a task, because the way the end user works with the user interface will radically change. Okay? And a plasticity at this level of abstraction, final user interface, means that instead of interacting with a user interface, for example, coded in HTML, you interact with exactly the same user interface, but coded in Java. So you see the impact for the end user is ridiculous. For the developer, he had to redevelop the user interface from scratch, but that's not a problem for the end user. Okay? So we have these levels of abstraction, the task, which is really the keyword in human-computer interaction, and the information that is needed, the structure of the user interface, the modalities, and then the programmation in terms of language and environment from the computer science point of view. And so if I go back to this word cloud in medicine, you see we had this notion of task. We have it in human-computer interaction. It is even the key word. It is a starting point in user interface. Creating a user interface without knowing the end user you work for and the task he has to do, it's not possible. It does not make sense. I teach human-computer interaction, and very often my students start by sketching user interfaces, and then I ask them, okay, who is the user? Oh, who is the user? And then, what is the task? Oh, what is the task? I don't know what is the task. So how can you design a user interface without knowing the user and the task? So you see, in human-computer interaction, that's really the starting point. We can't sketch user interfaces without knowing, of course, the user. That's the constraint. That's really the constraint we have for creating the user interface. And then the task. If the task changes, of course, the user interface radically changes. The persons of my family simply displayed in this way, but I can create a tree for have this fisheye menu that emphasizes the items the system predicts the end user should use. And so based on the prediction the system has, the fisheye menu emphasizes the key items. Here you have the frequency-based menu that reorders, reshuffles the menu, and of course the predicted ones come first. You have the morphing menus that deforms the items depending on the probability the end user will activate them. You have this menu, the smart menu that first presents the predicted items, and then you click here to get the other options in case the prediction is wrong, because of course the problem is when the prediction is wrong. When the prediction is good, perfect, the guy accesses to the right item immediately, but the problem is if the algorithm goes wrong, of course the system must make it possible for the end user to access the item he needs. And so you have different forms. You see these versions reorder, reshuffle the items. And there is another category of adaptation that uses time. Here, you just have the predicted items and you wait for 500 seconds and the other items appear. Here it's brutal, just the predicted items and then all the items. And the ephemeral menu from FindLater progressively pushes the items that were not displayed. And so you see this work combines space and time we have in medicine, but it's only short-term adaptation, whilst medicine covers short-term, middle-term, and long-term. So we have things to continue to work on. And so if I go back to this picture, in human-computer interaction, we are clearly focused on short-term. We do not investigate middle-term, long-term. So this picture will help us to drive our research in the future. One thing we have started to investigate is about persuasive technology. I don't know if you are aware of that. Persuasive technology means that thanks to technology, you will try to change the end user's behaviors or attitudes. For example, you want to help someone to stop smoking. If the guy is not motivated, the system will not work. Motivation is a strong requirement. Without motivation, the system will never work. But if the guy is motivated, then it's possible to use technology so that you help him in changing his behavior. And so the point is to couple plasticity and persuasion so that to adapt persuasive technology to the evolution of the end user, also for fun, because if technology is not fun, persons will not use it over time. And so we couple plasticity and a persuasive technology so that to make sense in health. For example, we have this prototype for stopping smoking, taking tablets, making sport. But it also makes sense in the domain of energy to help people to save energy. And so there are several domains, also education, to explain young people how to bruise teeth, for example. And so there is a large set of application. And so since 10 years, there is this international conference about persuasive technology, which is promising because the number of application is really impressive. And last research area I investigate using plasticity is creativity support tools. I use the algorithms we have in plasticity so that to automatically generate possible user interfaces, not as final user interfaces, but just to inspire designers. And so, for example, you have this user interface for chatting. And so we use genetic algorithm to make the user interface change. And at each step, we show alternative designs to the designers who can select parts of the user interface he likes. And we relaunch the algorithm so that to speed up the exploration of the design space. And so we take benefit from plasticity at design time so that to support the exploration of the design time. And so all this work is done with people from different backgrounds. I collaborate with psychologists, sociologists, designers, doctors. And really, I believe in cross-disciplinary research because the complexity we have to face is so huge now that I'm really convinced that it's not possible to address it alone. Too complicated. Voilà.
Thank you.
Thank you very much, Gaelle. So we have time for a few questions, maybe. Any questions from the audience? Okay, I'll start with the first. So first of all, thank you very much, Gaelle. Really interesting. I really liked, especially when you explained the problem that, well, we have plasticity of user interfaces, but this interplays with the plasticity of the user because he's learning too.
Yeah.
And for example, and now when you were talking in the end about the various stages where plasticity can affect, and that we adapt the interface to something, I guess that it's a problem when I adapt the interface to a user that has been repetitively using my system, right? Because I memorize things, and then I don't look anymore. I know where things are. So if things change, I actually have to destroy all my learning and learn again. How does this interplay? How?
We do not have theoretical answers. We have user study, and and we adapt accordingly. But yes, that's the open question. That's why we have this theoretical framework, so that to see how the two phenomena interact.
Yes. Because I thought that it was particularly interesting, and then suddenly I realized that most video games I play, because I like video games, are very contaminated with plasticity, right? Because it's a very complex control mechanism, but it teaches me one by one. It increases the number of functions I can use slowly over time and make sure that I've learned them. You know, first I walk,
progressive.
then I can jump, and I can only progress if I jump that rock.
So we have this
and then
concept
you're
of
pushing.
Do you know progressive enhancement?
No.
In computer science, we have this approach. In human-computer interaction, we have this approach of progressive enhancement. Look at that on Wikipedia, for example. And so you push a function progressively. And in general, you start with a minimal number of functions, the key functions, and you define the criteria as you want. It can be a level of expertise, but it can be a time or what you want. You push additional functions, and so you increase the scope of the application.
So for example, if we're developing software to be used by patients that are at home, this software could be plastic and to evolve as measuring if my patient is evolving his capacity, then it becomes more and more powerful.
Exactly.
but you don't do this decision immediately.
Exactly.
You say, let me get as much as I can from this patient, and it will adapt
Exactly.
automatically.
I had
That's
one
very
research
interesting.
with Vincent Nouget in Grenoble about this self-adaptation for rehabilitation. And really the point was to adapt the system according to the progress of the guy. And so the question was, is it good to add and add and add and add things, or we will depress the guy because each time he progresses, he gets additional things to do, and so we see we have no theoretical answer. We adapt and we change the rules dynamically depending on the effect on the person, and so we need user study for that. Okay. It's complicated.
Okay. Oh, one question. Well, there we go.
Thank you for presentation. It was very good. I'm a developer at an hospital. I develop a electronic patient record. Some of the context we use it many times, but I see a problem in the plasticity. If we look only to the user and don't look to the data, because if I'm a doctor and I see any kind of patients regularly and they have the same diagnosis, they have the same analysis, I'm looking to that always. But if came a patient that don't fit in those analyses, those diagnoses, some actions could be hide because I don't use them more, but they have to give me some data that was relevant in this case. For instance, if I'm a doctor in the emergency room, I only need to ask for transport once a year or once a month. If my icon or my action disappear from the screen or go to some place, it's very difficult because it's different from the other actions that I do. My actions are there and there. If disappear and I don't know, then I have a call. I don't know how to make a transportation request.
I completely agree with you. That's why this notion of controllability, intelligibility, and controllability are key. But we do not have the solution so far. For sure, the end user wants to get the control. Keeps telling that people want to keep the control over the adaptation. And so the point is to be capable of adapting the system, but at any time must be possible for the end user to keep the control and tell, no, I don't want this adaptation. So intelligibility and controllability, that are the key properties, but they are so challenges to implement. And so there are people who, so perhaps I go back to this because I'm pretty sure this paper from Fine Letter, you see here, this version, the split menu, here you have the predicted items, and here you have all the items in the regular way, and including item 5 and item 2. So the guy,
that's the way we use.
Yeah, so the guy looks at the adaptive part. If he feels happy with that, okay, he selects the item. If he doesn't appreciate it because he doesn't want to get adaptation, then he looks at this part, which is a stable part of the user interface. And so you see, but that's really an open question. This publication, 5 years ago or something like that, I do not remember, but it's a synthesis of all the way of presenting adaptation. And so the point is how to combine stability and adaptation, because we know that adaptation can alleviate people in some situations, but the problem is that they want stability too. So how to couple the two? And so there is research in the field to explore how it's possible to combine the two. For example, the split menu. You have an adaptive part and a stable one. But of course, we have this problem of scalability, because here you repeat the items. And so if we lack of space, it's not possible to duplicate all the. Really a difficult question.
We use this kind of adoption,
Mm-hmm.
but with adaptation, we use the favorite tags
Mm-hmm.
for every items, and user can select
Yeah.
the favorite one.
Okay. So it's controllability. You put the end user in the loop, and he decides which one he wants to get. Okay, thank you. It's a very difficult point.
Maybe a last question. We all want to go for dinner, and we all want our guests to go for dinner. So I think that's then it for today. Thank you, Gaelle. Thank you so much for your talk.
Thank you for the questions.
And so that's the last talk of this lecture series for this year. So let's end it by thanking again Professor Gaelle Calvary. Okay, thank you.
Thank you to you.
Okay. So this is also very interesting.